Yeah, really divide. Exactly. So now I got my idea. You put it in the right one. The county. You know, yeah. That's it. I'm really interested. All right, well, let's get ready to roll. All right, good day, kind people. How are we doing today? Just chilling, relaxing. All right, good. All right, so the last test is over. We got moving on to this next section right here. There is also spring break coming up, but we got to keep our heads down and keep our focus as we go ahead and we try and finish off this next section. Any general questions before we get started today? All right, cool. All right, so we are moving in chapter 6, and we're looking at the normal probability distribution. Well, what is it? That's just one of them. Oh, I guess no, there is next. All right, so the key thing right here is last time we did the binomial distribution, and the binomial distribution was a discrete random variable, right? Remember the idea behind a discrete random variable is that not anything can happen. The values happen at discrete values. Yes, the number of people who what did we do? I think we did the credit card number of times the credit card swipe was successful is 0 through 8. That's it. Now we're going to be moving into continuous random variables. And if our continuous random variables, any variable is possible. If I ask you, hey, what's your height? Well, on your driver's license, might say 6'1", yes? But the reality is you're closer to maybe 6'1 and a half. Well, 6'1 and a third. The reality is that you're not really 6'1 and a third, it's 6'1.3458, right? The number is just how much accuracy we want, but your height, people's heights can be any number between 0 and I don't know how 10 feet tall, the tallest person 11 feet tall. I don't know. But basically that's what people's heights are in between. Yes? And any numerical value between there is a possibility. And so because of that, your continuous random variables have a different flavor to them, as we're about to see. All right, so again, random variables are broken into two pieces. We have our discrete random variables, where each outcome is distinct, while we have our continuous random variables, where each outcome can be any value on a continuum. With me? For discrete or random variables, I guess I should hit the play button. Huh? For discrete random variables, normally we have little boxes that we can use to describe the frequencies. For example, they sampled 65 vehicles right here, and they looked at the emissions. So in other words, for example, look how much carbon dioxide they're putting out, or ethanol, or whatever is coming out of those cars. They picked one of them right here, and they looked at the outflow right here. So a certain kind of car, say 12% of them produce a very small amount of emissions. And then about 40% of cars, they produce a medium amount of emissions and so forth and so on. Yes? I could take that information right here and I can make them into really small ranges because again, the thing is that your distribution, the amount of particulate, it could be one, but it could be 1.5, yes? It could be 1.15 or it could be 1.015, right? And so I can break these into much smaller groups. And if I do this right here, I will get this shape coming out right here. Notice right here how each of these right here are just really, 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 really small bar charts. Questions there? When we have this idea right here, if I connect the bar charts right here with a smooth curve, this smooth curve right here is the probability density curve for this distribution. Okay? This probability density curve goes from a histogram to a curve. Now, when it comes to probability density curves, the way we calculate the probability is by finding the area between 2 points on the curve. For example, if I want to figure out what percentage of vehicles emit particulate matter between 3 and 4 micrograms, I just find the area that's shaded in this part of the curve right here. Now, one of the things is that we're not going to ask you actually find the area by hand. You're going to let a calculator do that for you. Yes? Technically, you need to take a course called calculus. Anyone taken calculus before? Five. Right? That's what you would actually need to find the area under the curve. But we're going to let a calculator do that for us. All right. Now, the area shaded right here represents the proportion. And of course, if the proportion, a proportion can be changed to a decimal, yes? And so therefore, this proportion right here will be the probability of, in this case right here, being between 3 and 4. Questions there? The reason why this ends up being the probability between 3 and 4 is there's a special unique value about the area underneath this curve. Where is my unique value right here? The unique value right here is that if you shade the entire curve, start at the beginning and shade all the way to the end, the answer is going to be 1. If you remember our definition for our population, for our distribution, is that when you add up all the probabilities, there must be 1. Yes? The way we see that right here is that the area underneath the curve must be 1. So in other words, if I ask what's the probability that the car releases 0 up until whatever number this goes up to, that percentage is going to be 100%. It's going to be 1. Yes? And thus, if I shade any small part of this area, this will be a percentage of 1, which would make it into a probability. Questions there? All right, so some key facts right here. For a continuous random variable, the probability that an event happens is 0. The probability I find a car that releases exactly 3 micrograms of whatever is going to be 0. The reason why is that it is extremely impossible to get exactly 3 micrograms, right? It might be 3.0001, it might be 2.99998, right? To get exactly the value 3, that's going to be basically impossible. And so because of that, if it asks you for a continuous random variable, what's the probability of x equaling a? The answer is going to be 0. Okay? Which is different from the discrete random variables where we got an answer, right? What's the probability that 5 of the jurors would be selected? That wasn't 0, yes? That was an exact answer, yes? When it comes to discrete probabilities, we never ask for the exact value. Or if we do, you should simply know that the answer is going to be 0. Instead, what we ask for is the region between 2 values. We ask you to shade a region between 2 values, and then you find the probability between those 2 values. Questions there? Another way to say this right here is that a line by itself has no area. You guys remember this from plane geometry back in the day? Oh my god. Oh my goodness. Am I giving you guys nightmares? I saying geometry out loud. One of those basic rules from geometry from way back when was that a single line has no area, right? You can't find the area of a single line because there's no width to multiply. Area is length times width, yes? There is no width, and so therefore the area is zero. And so that's another reason for why the probability of a single event is going to be zero. Okay, and why we don't look at probability of single events, we look at probability of events between two amounts. Because then we can actually have an area. Out of all of the possible probability density curves that exist under the face of the Earth, the most important one by far is called the normal distribution. Why is it called the normal distribution or it's called normally distributed? Why is it called normal distribution? It's because for some reason, this tends to be the distribution for things that we find in nature. Okay, if you look at people's heights, for example, people's heights are not normally distributed. If you look at, so in other words, again, so what we mean by normally distributed right here is that the mean is going to be the center of the distribution. So most likely people will fall around the mean. And then as you go further and further away from the mean, the less likely you are to less likely that your event is to especially occur. So in other words, people who are 7 feet tall, the probability that they're actually 7 feet tall is very, very, very small. But the people who are around 5'8", 5'9", a huge percentage of people will be around that age. All right. Look at the heights of say anything, growth rates. No, not growth rates. The age, average living age. Almost anything you can think of. It happens a lot in physics, chemistry, math, science, political science, all these other things right here. These things tend to follow normal distribution. And that's this is the one that we chose. There are many, many other kinds of distribution. There's a uniform distribution, there's a Poisson distribution, there's a geometric distribution right here, but this is the one that we study because it's the one that's most applicable to real life. You guys like real life? I read somewhere that you should make stuff interesting so students learn it better. Mm, mm, mm. All right. So the normal distribution, like I just said, it's the most important continuous distributions right here. The normal distribution is symmetric, right? Its peak will be the mean, and your probabilities taper off equally on both sides. So it starts out in the center and it tapers off, heading out in both directions. Interestingly enough, in theory, the model goes off onto infinity. So in theory, you can have someone who is 55 feet tall. But you know, that's a mathematical extension right here. The idea that something goes on to infinity in our universe. Does anything actually go into infinity in our universe? Anyways, I digress. Questions there? Many times we get data right here. The data does not look exactly perfect, but we have to remember our early discussions about collecting and understanding data. Data is never perfect because we're always taking a sample. We're not taking the entire population. But what we find right here is that most data will fall roughly a normal distribution. And so we say that they are approximately normal. Let's use that. This might be, for example, students' grades on a final exam. Most students will score around the average, but you get some students who will do really well, and you get some students who will do really poorly, right? But most student scores will be around this point right here, and then from there it will taper off quickly. Very, very few students will get, perfect scores Very, very students will get 10s and 20s. Right? Questions there? Again, another example of something that follows a normal distribution. The normal distribution is set by two key values. The first is the mean. The mean of your normal distribution sets the center of the distribution where the peak lies, and the standard deviation sets the spread of the distribution, how wide or how fat the distribution is. I have two normal distributions right here, but notice they have the same standard deviation, so they look the same. But notice right here, the means have changed, and so the peak has moved to this side right here. Questions there about the picture? I'm drawing a normal distribution right here. If you move the mean, the peak will move. Another key point right here is because it is symmetric, the mean, median, and mode will all be the same value for a normal distribution. And that's one of the things that you look for. They have a data set right here. Hey, what's the mean? Hey, what's the standard deviation? Standard deviation. What's the mean? What's the mode? What's the median? If they're all close together, that's an indication that this distribution may be normal. Okay? Questions there? The other thing right here that sets up a normal curve right here is the standard deviation. As the standard deviation gets larger, the graph gets shorter and flatter. As the standard deviation gets larger right here, the data points are more spread out, and so the peak is going to be lower for that graph right here. Does that make sense right here? Standard deviation right here. If the data is more spread out, I have more data spread out. Because remember, in both of these, the area must be 1, correct? The area under the curve must be 1. So if I'm spreading out my data, the curve itself has come down because the area, the amount of space it takes up, has to be the same. Questions there? The larger the standard deviation, the wider and flatter the curve is going to be. The smaller the standard deviation, the sharper and the taller the graph is going to be. You guys okay? How was you guys' weekend? Did you get an opportunity to relax? You're still saying, of course not. Spring break is in 2 weeks. No, literally, normally when I was at your age right here, I had one mantra that's going through my mind: make it to spring break. Just make it to spring break. That was my one mantra. No, no, because the whole bunch of work that's just slowly piling up, and you got to make it to spring break. That no, yeah. Oh, you guys must have an easy life. You must be taking like a stats class or something. Just showing up and just getting your A's, yeah. I don't know. It was crazy out there, man. All right. So let us investigate the normal distribution by giving ourselves some concrete values right here. Your normal distribution right here follows something called the empirical rule. The empirical rule says that if you start at the mean and you go out one standard deviation to the left and one standard deviation to the right, then that area will be approximately 68%. Another way of saying that right here is that 68% of the data is within one standard deviation. If instead of just walking one standard deviation away, I walk 2 standard deviations away to the left and 2 standard deviations to the right, so I'm talking about this entire area right here. This entire area right here will cover 95% of the data. So in other words, if I found the average height for students in this class, let's say the average height for students in this class was say 5'5", and I found the standard deviation was half a foot. 5'5" plus half a foot is 6, and 5'5" minus half a foot is going to be 5 feet. So between 5 and 6 feet, 95% of you should stand. If I say if you are between 5 and 6 feet tall, about 95% of you would stand in this room. All right? Okay. So again, I should write that down, I guess. Let's say, again, this is not exactly correct. Let's say the average height in this class is, oh, I gotta do that here, is 5'5". And then 2 standard deviations away is, let's say, half a foot. So that takes me to 5 feet over here and 6 feet over here. If I ask anyone between 5 feet and 6 feet to stand up, about 95% of us will stand. Right? Of course, this will work better if I had a larger class. If I had like the entire university population, it will be more easier to see than the 5% is left out. All right? Questions there? And if I go 3 standard deviations away, 99.7 of all the data is within 3 standard deviations, right? Sometimes they say almost all, but you do need to remember the 99.7%. Questions there? Questions there? So if I go to my good friend Salt, SALT. I go to my good friend Salt right here. I have a distribution showing up right here. Notice right here the distribution that's selected is the normal distribution. Remember, we had to go and change this to a binomial distribution. But now I'm leaving a normal distribution, and you can see right here it has the normal distribution curve right here. Yes? Now, if I switch this to between, notice right how it shades the values in between right here. And this right here is the mean for this distribution, which is 0, and the standard deviation is 1. So if I select right here, -1, and if I select right here, +1, like so. Oh, that's not +1, almost. +1, like so. Then from this graph right here, this is 0 right here, this is -1 to 1. I have shaded this region right here. This region right here is approximately 68% of the data. If I am 1 standard deviation away from the mean, 68% of the data is what I am covering. All right? Questions there? If I switch this to -2 and then 2, in other words, 2 standard deviations away, then notice right here, I've shaded a much larger portion. 95% of the data has been shaded. Questions there? If I shift over to 3 standard deviations away, 3 and 3, like so, you can see 99.7% of the data has been shaded. Questions there? By the way, one of the nice things about Salt right here is that it will put the standard deviations down here for you. See 0, 1, 2, 3, 0, 1, 2, 3. It will put the standard deviations down for you. So if I change my data set up, if I put the mean as 100, and I put my standard deviation as 10, it's like so. And if I look right here at the bottom right here, you can see how they have 0 down here. And then I have 1 and -1. And so therefore, the number 90 is 1 standard deviation away from the left. The number 110 is 1 standard deviation away to the right. Does that make sense? All right, because the standard deviation is 10 points. Yeah. And so if I go back over here and I put x is less than 90, and then greater than 90, and x is less than 110, this is 1 standard deviation away from the mean of 100, yes? The standard deviation was 10. I went up 10 and I went down 10, yes? And the probability is still the same. It's still 68%, approximately. Questions there? Comments? Queries? Concerns? So if I wanted 2 standard deviations away, I would need 120 and 80 will be my 2 points. If I wanted 2 standard deviations, If I wanted 2 standard deviations away, I would need 80 and 120 as my 2 points. Questions there? Common square is concerned. So if I tell you the mean and I give you the standard deviation, you can find the points that are my cutoffs, right? For my 1 standard deviation, my 2 standard deviations, my 3 standard deviations away. I can find those cutoff points. Yes? Yes? All right, cool. Well, that and you do need to memorize that, and you do need to memorize these points right here, 68, 95, and 99.7. You do need to memorize these values as well. Question there. All right, cool. This right way is a way of writing 3 standard deviations away from the mean. The mean plus 3 sigma means I'm going up 1, 2, 3. And then the mean minus 3 sigma, I'm going down 1, 2, 3. So this right here is within 3 standard deviations. This is how we can write it mathematically. Questions there? You don't have to be enthusiastic. You can raise both hands. One hand is enough to ask a question. No? Cool. This is just a different picture showing the same information on your bell-shaped curve. If you shade the middle, 68, shade 2, 95, and shade 3 standard deviations, 99.7. What you need to do is recognize those. When you're doing your homework questions, you need to look for this thing right here. If you see the words empirical rule, you have to use these numbers, not your calculator. I just showed you how to do it in SALT, right? If it says empirical rule, you use these numbers because your calculator gives you the answer to 4 decimal places, right? These are all to 2 decimal places or 3 decimal places, yes? So if you see the words empirical rule, you have to use these numbers exactly. Don't use your calculator. Don't use SALT. All right? The SALT answer will be 2 right. If you catch my meaning. Example. Assume that the height of college women are normally distributed with a mean of 67 inches and a standard deviation of 3.2 inches. What percentage of women are between 60.6 and 67 inches? Again, so to answer this question right here, I am going to draw a number line. And this number line right here represents the base of my normal curve. What will come at the center for the mean based upon the information that I was just given right here? What will come at the center for this right here? The mean will be 67. All right. If I go 1 standard deviation above, what's the score going to be? 1 standard deviation above. It will be 70.2. How did she get that? She added the standard deviation of 3.2. If I was to go 2 standard deviations above, what will that score be? It would be 73.4. And if I was to go 3 standard deviations above, that would be 76.6. Questions there on how I got those values right here. If I went the other way, if I am subtracting standard deviation, what would the score be? 64.2. No. Almost. You guys are allowed to use the calculators now. 63.8. If I was to go down 2 standard deviations, what would that be? 60.6. And if I was to go down 3 standard deviations, that would be 57.4. Questions there on how I got those numbers? Adding, 3.2 or subtracting 3.2. I can apply my curve above. So, and the question says right here, what percentage of women are between 60.6 and 67 inches? So I'll go 60.6 is right here and 67 inches right here. And so they want to find this area right here. And they want us to find it using the empirical rule. Any suggestions on how we get the answer to this problem? You can't use salt though. We can't. Any suggestions on how we can solve this problem without our good friend salt? We can't any add salt to the food. So sad. No, we don't have to do that. It's simpler than that. Okay, you guys remember that this thing is symmetric, yes? What does symmetry mean? The two sides are equal, yes? So if I told you this, if I went from negative 2 theta all the way up to 2 theta, and I tell you that was 95%, yes? And the question is only asking for halfway until I get to the mean, what's the answer going to be? Divide 95% by 2. And so the answer is going to be 47.5. And so approximately 47.5% of college women will be between the height of 60.6 and 67 inches. Because the empirical rule says that if I am within 2 standard deviations of the mean, the area is 95%. Now, I'm not expecting you to learn it. No, we just talked about it 5 seconds, so I'll keep reminding you. But that's where the 95 comes from. All right? Anybody else? Let's try another one. Oh, let me show you what they have, right? So this is the full thing right here. 6, 7 in the middle, 6.6 right here, and they want this area right here. And so that's going to be 2 standard deviations away from the mean. And since we know it's 2 standard deviations away from the mean, the full thing is 95%. We take the 95, we divide it by 2, and that gives us an answer of 47.5. So 47.5% of college women are between 60.6 and 67 inches. Questions? Cool. Example number 2. The Center of the Population Economics, the Center for Population Economics at the University of Chicago studied the birth weight of 652 babies born in New York. The mean weight, the average, was 3,215, and the standard deviation was 914. Assume the birth weights are approximately normal, approximately bell-shaped right here. Find the number who weigh between 2,301 grams and 4,129 grams. So just like before, I start with a number line. Yes? So I draw my beautiful number line right here. What comes at the center of this number line? Which is 3,250. You guys got your calculators? So what is going to be 1 sigma? So plus sigma. What's going to be 1 sigma above? 4,129. If I am 2 standard deviations above, that's going to be 5,000. Not 5,000. Oh, you guys just want me to do it? Because I was hoping you guys would help me out here. 5,023? 5,043. And the last one plus 3 sigma. 5,957. And I'm going the other way now. So we're subtracting 914 instead of adding them. So if I go down 1 sigma, it's going to be 2,301. If I go down 2 standard deviations, it's going to be 1397, 87. And if I go down 3 standard deviations, it's going to be 473. So my mean, I start here and I go this way and I come down this way. Oh, let's try that one again. There we go. So better. And they say right here, what is the number of newborns born between 2,301 and 4,129? So in other words, between here and here. Questions? What's the probability of being between these two values? What's the probability of being between these two values going to be, according to the empirical rule? It's going to be 68%. Yes? I am 1 standard deviation off. I'm from here all the way up here. I am 1 standard deviation off. Plus 1 standard deviation minus 1 standard deviation. So this right here is going to be 68%. So if the answer is 68% right here, what's the number of newborns going to be? We have to take the 68% and multiply it by the total number of babies. So what is 0.68 multiplied by 652?
443.
Multiplied by 652. I give this answer of 400 and how much?
443.
443.
Like the other decimal places.
No, we just round. Yes, yes. We're not going to have, no, we're not. I'm not going to be. And so we round to a nearest whole number. And so 443 children. Questions there? Or in other words, 68% of the 652 babies. Questions there? Might have to take this. They keep calling me. All right, so again, same question right here. The mean, your mean right here, and you get your 2 scores. We figure out that there are 1 standard deviation away from the mean. And since we know that there are 1 standard deviation away from the mean each side, that means that area is approximately 68%. And then you just find 68% of the 652 babies. And that gives us our answer, 443. Questions there? Questions there? All right, cool. All right, so that's the end of this section. We'll just go ahead and get started on the next section because we got time. Hopefully. All right, so but this right here takes us into the normal distribution and finding areas on the curve. Just adding right here using salt. So in other words, in the first section right here, when we're using the standard empirical rule, we just try and get you accustomed to the ideas of, hey, I'm trying to find the area under the curve, right? But now we're just going to use a machine to go ahead and find out all these areas for us. Back in the day, it was much, much, much harder. We had to use these pre-printed sheets where literally If the score was between say 0.5 and 0.8, you had to go look them up on the sheet and then find the answers. It was crazy. You guys are blessed. You guys have no idea. Yeah, I literally had to buy a book for this class called Probability Tables, and then you have to have it for the test. You had to look up all these. Anyways, normal distributions vary in one of two ways. The first is either the mean is going to change or the standard deviation is going to change, or both of them are going to change. Back in the day, they used to use tables to find areas under these curves. Like I said, we don't do that anymore. All right. Whenever you have a distribution where the mean is 0 and the standard deviation is 1, this is called the standard normal distribution. This is why when you open in SALT and you open up the normal distribution, there's a 0 for the mean and a 1 for the standard deviation, right? Because it's set up to start as your standard normal distribution. Okay, the mean is 0 and the standard deviation is 1. A score that comes with your standard normal curve is called a z-score. A score that comes from your standard normal curve is called a z-score. Your z-score represents the number of standard deviations you are away from the mean. The z-score represents the number of standard deviations away from the mean. A z-score that is negative will means that we were below the mean. A z-score that is positive means that we are above the mean. So if this right here is a z-score, this z-score will be positive. Your z-score is your number of standard deviations you are away from the mean. Questions there? Z-scores only apply to your standard normal curve. Z-scores only apply to your standard normal curve. Questions there? So if I was to head back to SALT, my good buddy SALT right here. Whenever you take a score, so remember the score we did earlier on right here, a mean of 100 and standard deviation of 10. And this 90 right here was one standard deviation below the mean. Yes? To look down here, the z-score calculation is -1 for that value. Okay? Remember how I told you that the SALT is nice. It puts us the number of standard deviations below for us. The reason why it's doing that because these are your z-scores. The reason why it's doing that is because these are your z-scores. It's labeling your z-scores for you. Questions there? So if I put in a totally different number, for example, if I put 135 right here, you'll see that the z-score right here will be 3.5. So I am 3.5 standard deviations above the mean. Questions there? For a standard normal distribution, they are the same thing, yes. But only for a standard normal distribution. Anybody else? Anybody else? Huh? Yeah, 10 is a nice number for us. If I put in a score of say 122, my z-score will be 2.2. That's 2.2 above the mean of 100. Anybody else? If you're above the mean 0, your z-score is positive. If you are below the mean, then your z-score is negative. The mean itself has a z-score of 0. Because I'm 0 standard deviations away from the mean. Yes. Yeah. Maybe, kind of, sort of. All right, so this right here is the formula for calculating the z-score for non-standard distributions. For example, we saw the distribution a while ago where the mean was 100 and the standard deviation was 10. This is how you calculate the z-score for a value. So let me use that example I just had a while ago. Let me write over here, the mean was 100 and the standard deviation was 10. So if I had a score of 120 and I wanted to find the z-score would be 120 minus the mean, divide that by the standard deviation, and that'll give us an answer of 1.2. So this is how SALT is calculating the z-score. Take the amount, subtract the mean, and then divide by the standard deviation. All right? Questions there? Questions there? Yeah, it's one of those famous formulas that you do have to memorize that will not be given to you on the test. For example, a woman whose height is 67 inches and the mean for the population is 64 and the standard deviation is 3, can you calculate the z-score for 67? So the way you do that right here is in SALT. You put in the mean, which was 67, was it? I don't forget already. The mean was 64, sorry. So you put in a mean of 64. You put in a standard deviation of 3. Let me switch to a left tail test right here, because that just gives me one number. And then how tall was the lady? 67. So I put the 67 in right here, and you can see that her z-score is 1. If I go over here to the picture, the mean, the 64 is at the center, and your 67 is exactly 1 standard deviation above the mean, right? 3 points higher, right? Go from 64 to 67, and so her z-score is 1. Okay? If you wanted to use the formula instead of SALT, wrong place. If you want to use the formula instead of SALT, what you do is you just plug it into this formula right here. So that's going to be 67 minus 64 divided by the standard deviation. Again, we get the same answer of 1. Questions there? By the way, this is called standardization, taking the score from a mean of 64 and 3 and changing it to a mean of 0 and 1. We can see this right here. Notice right here that this graph right here, the scale is larger. And so that means that this graph is more spread out. Yes. But if I take the score of 67 and in a standard model, I take a score of 1, notice right here that I'm exactly at the same place on the 2 curves. Questions there? Comments? Queries? Concerns? Hopes and dreams? Stories about how your hair fell off and you don't know how to get it back. Like me. You guys heard what happened once? I was just walking down the road, my business, and then there's this lawnmower, right? And I was walking, right? And then there was this lawnmower, right? Right? And then I tripped and fell, then poof, I barely survived. No? Yeah, that's what happened to me. Oh, I tell you. All right. Another z-score example. In a particular year, on the ACT, the average was 22.4 and the standard deviation was 5. While for the SATs, the average was 515 and the standard deviation was 122. Jill scored 28, Jim scored 546. Who did better? Or relatively speaking, who scored better? Right? This is one of those classic examples where you cannot just look at the score and say, hey, 546 is larger than 28, so therefore Jim scored better. Yes? What you need to do is consider the distributions mean, and standard deviation. And so in these situations, what you do is you first find the z-scores for the individual students. And after you find the z-scores, you can then compare to see who is further away from the mean. Does that make sense? And so I'll show you how to do insult. I'll just let them do it for us. We use our fancy formula. So for the 28, her z-score was 1.12, while for the 546, his z-score was 0.25. And so that means that Jill did better. Think about it this way. The average was 22.4, and Jill was 1.2 points higher than the mean, while basically Jim was just a little bit higher than the average score for the SATs, only 0.25 standard deviations higher. And so therefore, clearly, Jill did much better than him. Yeah? Questions there? All right, so that's where we will stop for today. Any questions? All right, let me go ahead and take attendance.